And thanks to our wonderful teachers and counselors and for taking the time on a weekend to be with us here at CSU today. So Karan, gave a nice introduction on some of the work I do here at CSU with some of the background of my previous education back at Minnesota and the University of Illinois. And he gave me a nice hint of how I might kind of connect some of the discussions on resilience and bouncing back in education as it relates to community resilience. So I'll try to make that connection, Karan, as I proceed. All right, so I'm going to give you a little bit of background about myself to see how me on a personal level managed to change kind of a little bit my emphasis over time. I started back at the University of Minnesota from 1999 to 2003. I did my undergrad there, and I did my master's. And I was working a lot in the lab on testing structural systems. And my master's degree was related to fatigue cracks in oil tanker ships. It was a project sponsored by the US Navy. Following my bachelor's and master's, I went to Lehigh University in Pennsylvania, and I started to work on fatigue cracks in bridges. How do we actually repair bridges? How do we inspect them, and so on? And I spent quite a bit of time there. Then I switched gears a little bit and went to the University of Illinois in Urbana-Champaign, and I worked again in the lab on how to actually run structural testing using pretty complicated systems. Where you can see this orange blue boxes are more like a shake table that is boardable. You can move it anywhere. And I continued that work and ultimately did my PhD back at Illinois. Again, doing structural testing, steel structures, and employing maybe advanced testing protocols. But then, since I came to CSU, I started to shift gears a little bit. And my work at CSU has been focused primarily on resilience and sustainability. And in the process of trying to look at them individually or combined, we have to look at many different things. Societal constraints, economic constraints. Maybe we have to look at how the structure is damaged after an event. And so that ties really well with my background. And how communities recover following natural disasters, as Karan indicated. And to be able to do this, we have to develop tools supported by mathematical theories that allows us to actually do this complex analysis, which I will reflect upon a little bit. And so to reflect on this kind of some of the things that we've been doing and how it ties to STEM education in general, I've outlined the presentation, structured the presentation in a way that first it starts with the motivation. And of course, you guys are the experts, so I'm not going to dwell too much on motivation for STEM. But what are the current and future trends in STEM education? And how do these current and future trends actually relate to some of the work that we're doing here? I will give an example of some of the work we're doing on wildfires and then recovery from natural disasters. And I will conclude with some thoughts on what would be the characteristics of future engineers. What else are we missing? If you look at the literature on current and future trends in STEM education, are there enough? And the answer is definitely not. So if you look at the motivation, and if you look at, and I did that actually looking online in preparation for this talk, you'll find that people talk about hands-on experience, maybe making science and math fun for students to learn, maybe develop collaboration skills. And one of the things that are also mentioned, which I think is really important, is developing logical thoughts. How do you actually think about a problem and try to solve it? And one of the most important things, in my opinion, is how do we teach students to get to the point where they can develop logical thoughts for any problem. This way, they reflect on it and they're able to address it in an unexpected way. But you'll also find the literature speaks of economic competitiveness, which is definitely important. It's a matter of a national security that we have to think about. Countries are definitely surpassing us in terms of STEM education, and that what that means is that they will be able to compete much more in global markets. And we cannot, from a national security perspective and economic competitiveness, we cannot afford to fall back behind. But what I want what I want from a STEM education, I want the students to be more, to develop insight on complex problems facing our world. The good news is that when I run into, kids, you say 11 years to maybe 15, they talk about climate change, they talk about global challenges, they talk obviously about the pandemic. They're thinking that level, but we want to get them to the level where they can actually think logically about plausible solutions. So to me, it's not improving their math. It's not necessarily economic competitiveness. I want them to be able to think about complex problem in a way that has not been thought about before, because that's the only way we can solve them. And how do we address these problems? Of course, the underlying assumption here is that they have to be equipped with proper math knowledge and science knowledge to be able to address these problems. So if you look at the trends in STEM education and how we might be able to take these trends and translate it into research so that students who are taking classes with you guys are ready to hit the ground running and be able to solve these problems moving forward. And you'll find that these are trends that you'll find actually in the literature. So hands-on learning is very important. STEM in all subjects is really important. Utilizing robotics, games in STEM. And they all evolve around the idea of improving innovation and creativity, motivating students to learn, and so on. If you look at future trends, people talk about, instead of focusing on STEM, we integrate art with STEM. So they call it from STEM to STEAM. Cross-disciplinary thoughts. How do you actually take ideas from different topics and integrate them together, for example? Adaptive learning is very important because people learn using different approaches. Some people learn much, much more when they're able to actually look at the problems and visualize it. And of course, entrepreneurship is really important because it emphasizes soft skills as well. So what does that mean in terms of using some of these concepts for research in general? Well, I want to hint, or I want to show you some of that stuff, because this stuff is really important. If you get the students at your end to think about how to integrate some of these concepts into their teaching or into their learning, then they're able to actually address these complex problems when they come to college in an easier way. So take, for example, wildfires. It's a global problem. And what I like about wildfire, despite all the damage, of course, and all the losses, which are very unfortunate, it's the fact that it's a global problem. Students are thinking big picture, because I want them to think big picture and then zoom in on the details later. It's a big problem that impacts all continents, not just the US, of course, or North America. Wildfire is a problem comprises of these different stages, and of course at Colorado we're not stranger to this particular natural disasters. We have fire ignition, we have propagation, we have embers attacking our homes, and we have fire propagation within communities. The losses have been so high. Every year we hear of losses around the country, and we haven't been able to find a solution yet. Now, take, for example, as I mentioned, games in STEM, the concept of game theory, which you can utilize what's called cellular automata, which is a branch of game theory. We can take something like that to model wildfire. So imagine you're teaching students how to learn math using cellular automata, or what cellular automata is about to begin with, and get them to think at that level of maybe employing games to learn the math, or employ different game theory in the science classes. They come here ready to think similarly, ready to hit the ground running if I tell them, what can we use game theory to do something here? So the way this works is that actually you start with an initial state. You see the top row here of a circle and star, a triangle, and so on, and you just specify the rules of how you want to change the initial state to the next state. So in this case, the color green goes to the left, for example, and the shape of the star goes to the right. And this cellular automata approach is what used to actually develop games. And we use the same approach to model wildfire propagation in communities. What that does actually also gets the students really excited about this, because they feel like they're playing video games. They're not necessarily, being told to find a solution to the problem. That's not the only thing. And so the idea here is that we model the wild land with these cells. So you can see the green cells represent vegetation. The water cells represent water, essentially the blue cells. And then the fire intensity varies from 1 all the way to 3 down to 0, right? And using this rule-based approach, we managed to actually do something like this, where we can model, this is a plan view of a wild land. And then we can actually model fire propagation in the wild land and how the embers are landing in the wild land, starting new ignitions. And on the right-hand side, you see we're tracking actually the ember trajectory. It's an interesting approach to model wildfire propagation and behavior, and at the same time, it would actually capitalize on how you taught the students some of these concepts in high school. But the problem is actually much more complicated than fire propagation in the wild land. We've seen how communities are destroyed, and to date, or until very recently, there were no models that allows you to actually capture or model damage to the built environment in communities. So we wanted to develop a model for that. So we looked at cross-disciplinary research, borrowing from another field, which is something you have taught the students to learn, and we start to look at how disease transmits in social network. So COVID-19 transmission, for example, is very, very similar to wildfire transmission in communities. Mapping structure surroundings is very similar to contact tracing. Clearing defensible space is very similar to social distancing. Hardening a structure is similar to vaccination, for example. Creating a buffer zone is similar to closing the border. So can we use these concepts? Can we borrow from different fields to model wildfire damage to community? And I want the students to have the flexibility in their mind to be able to do this without feeling very, very constrained by the fact that, no, this is epidemiology and it's not related to structural engineering, for example. So if you look on the right-hand side, you have a community that is shown in green with wild land surrounding, and these different colors of yellow, orange, and so on represent fire intensity, as I showed you on the previous slide. So we first have to identify the nodes that are close to the community, and then, or close to the fire, which is the red nodes, and then all other objects, all other structures represented by nodes as well, and then the middle one is the one I'm interested in. So I develop my graph, and I run my actually analysis to figure out what's the likelihood of fire transmitting from one of these red nodes all the way to the blue node. And this is the same way we do disease transmission analysis. There are other models, but this is one of the ways we look at disease transmission in a social network. And the result of this, us borrowing from disease transmission, for example, to model community fire, is the ability to finally model fire damage to communities. And this is the only model that exists that actually can capture wildfire damage. So we ran the model for the campfire. We got 85% to match. What you see on the left here is that disease transmission model that we developed by borrowing from another field. And what you see on next to that in the middle is us taking the vulnerability level and converting that to damage versus undamaged. So blue means undamaged, and the red means completely damaged. And what you see on the far right is observation from the field. And the match between the observation in the field and what we managed to calculate is quite strong, right? That would have not been possible if we were so stuck in our mind saying that the only way you can model fire propagation in community is to use the concept that is called computational fluid dynamics, right? If that was the only way, and many people are doing that, we would have been stuck, no solution. But the fact that we were willing to think outside of the box allowed us to come up with that model. Because we live in Colorado and we all care about Colorado, we ran the analysis for the recent Marshall Fire, and we managed to get 72% match. And we are so excited because I think this is going to open the door to solutions to wildfire in communities, not only in Colorado, but also in the Western United States. So this is one, again, example to show how cross-disciplinary research might be very beneficial. And if you teach the students the material in that sense, it will benefit them tremendously when they come to college. Another example I want to share with you also is recovering from extreme event. That's an area we've been working on heavily here at Colorado. And of course, natural disasters are pretty evident everywhere around the country and around the world. You've seen the recent earthquakes in Turkey and Syria. Very unfortunate, but it's the fact that we deal with now. And of course, these natural disasters are have their tolls on communities. It's the picture might obviously is devastating, but changing from extreme destruction to the community building back like this is obviously very complicated. And so I'm going to try to simplify that complexity by showing you an example of what that means. Let's say this community was hit by an earthquake. And then that earthquake was followed by fire, which is something you would see on the West Coast, fire following earthquakes. And we're trying to recover these buildings. These buildings are damaged heavily. And because they're damaged, then we have economic losses. And these economic losses come also with some sort of social losses. People will have to leave these buildings and go live elsewhere. And maybe they'll rent, find a hotel, live somewhere until these homes are fixed. And once we fixed all these homes again, then people might have the opportunity to either come back to their homes or go elsewhere because they don't want this community anymore. Of course, the problem is much more complicated than this, but in order for us to model it, we have to think outside of the box. And we start by looking at the interdependencies and the linkage between all these different community sectors. You have to actually recover the buildings, you have to recover the water, the transportation, the communication, every single thing, and not just the structure itself, but people who use these structures or work at these infrastructure as well. So the whole idea here is that this interdependency is complex and we have to capture it, but that's not the end of the story. There are too many angles to this that allows you to predict recovery. You have to know how many repair resources and how many people can repair your structure and who's available and who's not. Can you get help from outside the community and so on. So the interactive or adaptive aspect of modeling a complex problem like this allows the student to actually see beyond an abstract of community being damaged and then community recovery. So this is, for example, a recovery simulation that we've done for the Port of Mobile, trying to look at ports recovery following hurricane events. And so this on the top left is actually the Hurricane Katrina coming in on the community. So, and then you can see actually next to that, again, the representation of the water level within the area. On the bottom two left figures, you see the inundation in Mobile, and you also see the water level at the Port of Mobile. And then at the top right, you see damage to the port, and then our recovery model of the port. So recovery is very important. We need to figure out how long it would take for the port to come back and operate. This very complex analysis requires network simulations, requires you to understand element of social science, element of systems engineering, elements of computer science, elements of structure engineering. Too many things actually that integrate together. And by the way, I did this with my students who are also structure engineers. We didn't have to really go out and find people to collaborate with to be able to do this. We could, I mean, it would be great to collaborate, but I'm saying it's not, because once you open their brain cells that every single thing is possible, you can borrow from other fields, you can learn other concepts, they can do a lot of things with tremendous confidence. We did the same thing, modeling hospital recovery following extreme events. And this is Shelby County that has 22 hospitals, and these hospitals, the whole community is struck by an earthquake, and we're trying to look at how many beds are recovering, and what is the total number of beds, and what is the waiting time, average waiting time, which is that W sub T, and the hospitalization service, how long it's taking to come back online. And you can see these gray areas changing on the map because it reflects that certain areas are perhaps the service area for some hospital is changing as a function of fixing the roads, fixing the homes, fixing the power, and so on. So it's, again, very heavily complex analysis. But through this interactive modeling approach, we're able to reflect much more and come with solutions. We're actually right now doing work for the World Bank, looking at healthcare resilience in developing countries. So it became useful at the end of the day. But then I don't want the students to stop at this point. We're solving complex problems, yes. We're excited about these recovery models because they have never been developed, yes. But there is more to it than that. So if you look in the literature, for example, you'll find that people talk about resilience and say there are potential resilience metrics that we would like to recover. So I showed you the recovery of the port or a network of hospitals. So infrastructure recovery could be one of them. But there's economic recovery, employment rate, physical impact, business interruption. There is actually also social, which could be population dislocation or out-migration or other things. There's two things here. Communities get to decide which ones they want to recover, right? So communities, and usually it's agreed upon, which drives me nuts when I hear that word, it's agreed upon that communities get to pick one or two metrics to recover. That's number one. Number two, the recovery curve is what you see on the right-hand side. So if I want to recover, for example, employment rate, what you see on the right-hand side, the functionality or the employment rate will be a specific value. Then the event hits, right? Let's say it was a tornado, then it will drop, then the functionality will drop, but then I can recover it. I can recover it by fixing businesses and so on, and many other things. I can do certain things, is what we call adaptation, to be able to recover even faster. And if I work ahead of time before the event, in anticipation of the event, I can actually make the recovery even faster, right? So communities get to pick. The recovery looks the way I showed you here on the right-hand side. And of course, the damage or these losses on recovery are driven by infrastructure damage to the community. But who says that any of that is actually correct? We started to ask, and I want the students to do that. Don't take the status quo and say this is the way it is. This is not the way it is. So why do we have to select one or two of these matrices, and who decide on these? Why is the recovery a smooth curve? And what if disruption is driven by social disruption or economic downtime, not just infrastructure damage? And when we started to ask these questions, of course, we didn't come up with the answer right away. It took us a while to really think about it. But I can tell you, truly, one of the things that helped us very much coming up with a solution is turning to Gotham City, the city of Batman. How many people watch Batman movies? So me and my student would watch we watched all the movies, and we would meet on weekends and have coffee and talk about the movie. And his name is Akshat. Akshat is a very polite guy. And he says, "Sir, did you see when they brought Gotham down by an economic disruption?" I say, "Yeah, Akshat, that was wonderful, because that's what we want. We want a model that can take infrastructure damage, economic downtime, or social disruption, right?" So we looked at Gotham, and of course, started to watch all the movies.
You attacked Gotham before?
Of course. Over the ages, our weapons have grown more sophisticated. With Gotham, we tried a new one, economics.
So we felt we're on the right path here, right? Because Gotham has been brought down by economics downtime before, right? So that's wonderful. And then, by the way, I'm originally from Egypt, so of course Arabic is my main language. So Russell rule, if you're not sure what that means, it means the head of the monster. I don't know why they're using it in the movie, but in case you're wondering, that's what Russell rule is. And then we saw this.
Storming Blackgate and freeing the oppressed!
And we got really excited, because now we're watching the movies that have natural disasters, and it has economic downtime, and it has social disruption. So we started to think, okay, can we develop a model that can actually do the same? And this is also possible because I let my students on a personal level to do whatever they feel like doing. I just never tell them you must do 1, 2, 3, right? And if they want to look at Gotham or look at Batman, I have absolutely zero problem with that. So we modeled Gotham City, but we again borrowed, not just going from STEM to STEAM, integrating art into our analysis, but also actually we borrowed from what you see up there is the equation of motion for a structure subjected to dynamic excitation. We use this equation that you see at the very top to actually model buildings subjected to earthquakes. But instead of M being the mass of the building, and C is the damping, how much damping you have, and K is how strong the building is, we actually use the math as the social vulnerability, C as the economic stability, and K as infrastructure stability, and F is my damage function. And then we said, let's hit Gotham by social disruption. We got really excited because Russell Rule opened these gates, and everybody ran out, and then hell broke loose. So we wanted to try to do the same. And so in order for us to do the same, we actually modeled Gotham City. And Gotham is nothing but lower Manhattan, which was actually pretty cool too. And you can see our Arkham Asylum, which is the island at the bottom left. That's where the jail is. So it's isolated, and that's where they put the jail. So we modeled it using this new finite element approach. Now the mathematical background of the student became very important. It became very significant in being able to develop this mathematical, what we call grid on the right-hand side that allows us to model Gotham as a finite element model. And in the process of doing that, we can hit Gotham by social disruption, we can hit it by infrastructure damage, or economic downtime. Furthermore, we actually can now model recovery, and it's not a smooth curve anymore, right? We don't have to actually have a smooth curve. It can be whatever it wants to be. And it was really interesting that when we hit Arkham Asylum by social stability, we actually saw that the entire Gotham City is vibrating to that social stability, not just the island, which was pretty cool. And here's the resilience order. The other thing is that you don't have to pick one or two things to recover and say, I want to recover from that. This model allows you to integrate. You can look at things individually or integrate everything together. So we had to challenge the general status quo out there to be able to do this. You know, I'll tell you something really exciting. We're pushing this model a little bit to a level now, which we didn't think about at the beginning, that if it holds true, we would have probably the answer to be able to solve or understand failure path or failure mechanisms in any system on planet. So we're really excited. We're working on that now. If it works, that's going to be really cool. But it would have not been possible if I did not push the student to be able to do this. Of course, we always get tremendous and wonderful support from our College of Engineering, and so the college wrote a nice article about Batman and Gotham City, and there was a lot of tweets, and it was really exciting to see Batman himself tweeting about the work, and you can see at the bottom here. But this was very rewarding for the student too, because all of a sudden he sees his work all over the place and all over Twitter, and exciting. And he was really having a blast saying, hey, did you see this tweet or that tweet? And getting the student excited is, in my opinion, also an art, right? It's not just, here's some equations, go solve them. You gotta get them engaged, and that in itself requires also a way to do that. So I tried to show you kind of some of the trends from current and future trends in STEM and how we can make parallel with research. But I want to emphasize at the very end that something is missing still. We're not necessarily done. And I'm not putting pressure on you guys to look into this, but it's something we definitely have to look into together. What's missing? I was recently invited by the National Academies, US National Academies, to be part of a early and mid-career group from across the country to kind of discuss and talk about very important issues facing the country. And this is, by the way, the Einstein statue in Washington, D.C., next to the National Academies. And one of the things we've done as a group is to write this paper that came out, it's an editorial paper that came out maybe 3 months ago on the climate changing and engineering education needs to change as well. We made the argument that there are 4 things that are essential for us to be able to address climate change that go beyond what you're teaching the students and what we're teaching the students to. So for example, we have to understand how climate and sustainability and resilience are all linked together. We're not doing that when we teach the students in civil engineering. We have to look at a wide range of disciplines and how we integrate them into solutions. Equity and equality are very important. We have to address these concepts because it's evident that we've made mistakes in the past when we ignored these concepts, for example. We have to understand the ethics and justice dimensions of engineering. And of course, COVID was a perfect example of what that might imply. And we have to collaborate with diverse communities because communities understand their needs more than us, but we have to be able to work with them to address these needs. So I'll give you a quick example that relates to some of these concepts. One of my students recently did some analysis on Mobile, Alabama, and we looked at all buildings within Mobile, Alabama. We started to think, actually, if you look in the literature, if you listen to the news, people talking about, a hurricane event that hit a community, you always see the damage to the buildings above ground. But we started to think about the sea level rising and impacting the foundations of buildings. Coming from underneath, everybody's sleeping in their beds, no one is caring about that, and 50, 60 years later, you find that you have major problems with your buildings. And when we ran the analysis, we found that the cost associated with the sea level rising and the corrosion essentially damaging your foundation is 3 times that of expensive soils. Expensive soils already cost us $2.3 billion a year. So, of course, you ask, well, why was this ignored, right? How come, am I the only one who thought about this when we wanted to push in that research direction? Absolutely not. But there's no way, right? Because it's not that difficult of a problem to think about initially. So we started to ask the questions, why was this not considered in the past? Was there a lack of understanding the link between sustainability and resilience? If you prefer, referring to my previous slides, was it a matter of ethics? Ethics is really important. How are we teaching our students to integrate ethics? Is the designer just worrying about initial cost and the profit they're making on the spot without any consideration to how much this might cost the owners down the time, 30, 40, 50 years from now? And who pays to fix these homes then? If the person who made all the money is now gone, how should we consider equality versus equity if resources are limited? What are the consequences of bias selection? And should we work with the community and let them decide which home gets fixed? For example, if you have schools and hospitals which are vital for community stability, maybe we fix homes first for people who work at schools and hospitals before we start to fix other homes. And this is just one example. And because we thought a little bit outside of the box, Yale Climate Connection wrote a story about it. And the thing that, of course, it was nice to see that story written about the work. But it was also, I kept thinking about it. We're asking the student, how come nobody ever did this work? Why? I still don't have an answer. But we need the students to be able to think outside of the box and start to actually think along these different dimensions. And finally, I will just conclude by saying that we definitely cannot solve our problems with the same thinking we used when we created them. Albert Einstein was very wise when he said this, and I wholeheartedly agree. We rely on you guys to be able to educate the students in a way that when they come here, at least the brain cells are open up to address these complex problems. Karan mentioned early the issue of recovering and the issue of being able to bounce back, even bouncing back from an education problem perspective. I will give you something, actually a personal story on that regard. When I came to the US back in '97, I came on a tourist visa. I didn't speak a single word in English, 0 English, it was none. And I wasn't really the type who cared about school too much when I was back in Egypt either, right? And I bounced back from all of this until I managed to have a career. So what I'm saying, it's not late for us to do something for our students. If there's an issue with the students, we can fix it. They don't have to be on the right path day one they got into school. If it's too late, if they think it's too late, it's not too late. We can work with them, we can work with you guys to figure out this problem that we're having. And finally, I just want to thank all the students. This work was done by students, not me, so they do all the heavy lifting. And of course, we've been supported by lots of funds and from different organizations. So I want to thank them also for that. And thank you so much for listening to the presentation.